Good morning, all. I welcome you all at online lecture portal of IIMT College of Engineering. I am Ashish Kumar Singh, working as an assistant professor in Electronics Communication Engineering Department of IIMT College of Engineering. Today, I am going to present a lecture on three-phase induction motor. This lecture includes the following topics, and the topics are introduction. In this topic, we will discuss about the basics of three-phase induction and then construction of three-phase induction motor. After completing construction of a three-phase induction motor, I will discuss about working principle of three-phase induction motor. In this topic, we will discuss on which principle three-phase induction motor works and how it rotates. After completing working principle of three-phase induction motor, I will discuss about the term slip, what is slip, and how can we solve numerical based on slip. Then thereafter, I will discuss about torque slip characteristics of three-phase induction motor, how torque varies when slip increases or decreases. And after completing torque slip characteristics, I will discuss about the various advantages of three-phase induction motor and disadvantages of three-phase induction motor. After completing all this topic, at the last, I will discuss about the various application of three-phase induction motor. So let's today's lecture, introduction of three-phase induction motor. As we know that three-phase induction motor are the most common machine used in industries, and these machines are used in industries because of the following features. The first feature is it has very simple design. Second feature is it has rugged construction and its cost is very low as compared to other AC machines, and its maintenance is very easy. Then thereafter, the second feature due to which it is used, it is available in wide range of power rating from fractional horsepower to 10 megawatt motors. So we have a very large range of machine in three-phase induction motor. And other advanced features, most important feature is that it runs essentially at constant speed from 0 to full load, and there is some disadvantages associated also, due to which we are using other electrical machines, and its main disadvantage is it is not very easy to have variable speed control. So let's start about the construction of three-phase induction motor. As we know that all electrical machines, mainly running motors and generators, mainly consist of two parts, same as an induction motor has two main parts. One is stator and second part is rotor. As we know that stator, the stationary part of three-phase induction motor is known as stator. It may consist of yoke, inner steel frame, three-phase stator winding, and three-phase stator winding. So it consists of a steel frame that support a hollow cylindrical core. The core constructed from stacked lamination having a number of slots, and we provide three-phase stator winding in these slots. The three-phase winding may be connected in a star as well as delta winding, that depends on the power rating, power required. Now we will discuss about the rotor. As we know that name suggests, the rotating parts or revolving parts of motor is termed as a rotor. It is composed of punched lamination stacked to create a series of rotor slots. In these rotor slots, we provide either rotor windings or rotor conductor bars. Depending upon the winding or conductor provided in these are these rotors are subdivided into two categories. First one is wound rotor. It is a conventional three-phase winding made up of insulator wire similar to the winding of the stator, but as we know that in a stator we may connect three-phase winding either in a star connection or delta connection, but in wound rotor case we provide we connect three-phase rotor winding in only star connection. Second one is a squirrel case rotor. In this type of rotor, we place aluminum or copper bar in rotor slots, and these copper conductors or copper bus bars are short circuited with the help of end rings at both ends that forms a squirrel case shaped circuit. That's why its name is given squirrel case rotor. The two basic design type, depending upon the rotor design we use, they are further subdivided into squirrel case induction motor or phase wound induction motor. So squirrel case rotor, this is the constructional diagram. The figure shows the squirrel case rotor diagram. A squirrel case rotor is a rotating part of common squirrel case induction motor. It consists of a cylinder of steel lamination, and the rotors, this cylinder, outer periphery of this cylinder slots are cuts, and in these slots we provide either aluminum or copper conductor embedded in this surface, and at the end they are short circuited with the help of end rings to form a closed circuit. Second type of motor is three-phase wound rotor motor, phase wound rotor motor. It is also known as slip ring rotor motor. In this three-phase star winding is placed in rotor slots of a rotor, and these windings are brought to the three slip rings. It can be the rotor windings are connected through slip rings to external resistance. It can be started with low inrush current by inserting high resistance into the rotor circuit externally. This is the constructional diagram of three-phase induction motor, where we saw that various parts of three-phase induction motor. It consists of shaft key, motor shaft, bearings, stator, mounting holes, enclosures, base, rotor end rings, fan cover, cooling fans, non-drive end seals, stator winding, rotor, eye bolt, and rotor bars. Cooling fans and is used for cooling the rotor conductor or dissipating heat produced due to the various losses in the motor. and fan cover this fan assembly so that it is safe for working personnel. Now, after discussing the construction and types of induction motor, we comes to the next topic, that is the principle of operation, on which principle three-phase induction motor works. So, three-phase induction motor works on the principle of Faraday's law of electromagnetic induction. Faraday's law states that whenever a magnetic flux changes with respect to conductor, an EMF is induced in the conductor. There are two types of magnetic induction. First one is self-induction and second one is mutual induction. So, three-phase induction motor works on the Faraday's law of it works on mutual induction, same as transformer. What is mutual induction? When a coil or conductor is brought near to the current carrying conductor, an EMF is induced on second coil due to the change in primary coil. So, in three-phase induction motor, when three-phase AC supply is connected to three-phase stator winding, a rotating magnetic field is produced by this three-phase stator winding in the air gap present between stator and rotor. And this rotating magnetic field rotates with synchronous speed in the air gap that is given by Ns equals to 120 F upon P, where F is the supply frequency and P is the number of poles. And Ns is called the synchronous speed of the rotating magnetic field, that is measured in RPM, that is revolution per minute. And the direction of rotating magnetic field depends on the phase sequence. We can easily change the direction of rotation of rotating magnetic field by changing the phase sequence. This rotating magnetic field cuts the stationary rotor conductor and produces an induced voltage in the rotor winding according to Faraday's law of electromagnetic induction. Due to the fact that rotor winding are short-circuited at both ends, so this rotor conductor forms a closed circuit. Due to the closed circuit, an induced current flows in the rotor winding, and according to Lenz's law, this current tries to oppose the cause due to which it is produced. Since the cause is the relative motion between rotating magnetic field and a stationary rotor conductor, so to oppose this cause, rotor start rotating in the same direction in which rotating magnetic field rotates. The torque is produced as a result of interaction of these two magnetic fields, that is the magnetic field interaction between the magnetic field produced by stator winding and magnetic field produced by the rotor winding. So, torque produced by induction motors depend upon magnetic flux density of rotor as well as flux density of stator, where tau index is the induced torque and BR and BS are the magnetic flux density of rotor and stator winding respectively. Now, as we know how this three-phase induction motor runs, we will discuss what happens if induction motor runs at synchronous speed. Can induction motor runs at synchronous speed? If yes, why? If not, why? As we know that three-phase induction motor is work on Faraday's law of mutual induction, and according to Lenz's law, rotor rotates due to the relative speed between rotating magnetic field and stationary rotor conductor. So, comes to our question, can the induction motor runs at synchronous speed? Which answer is no. The induction motor does not run at synchronous speed. Then why? As we know that induction motor does not run at synchronous speed. If rotor runs at synchronous speed, what happens? The speed of rotating magnetic field of rotor and rotating magnetic field will become equal, so there will be no relative motion between rotor and stator rotating magnetic field. Due to this, no conductor cuts the magnetic line of forces, so there will be no induced EMF at rotor conductor, and when induced EMF at the rotor conductor will become zero, so the induced current on rotor conductor will also become zero, and when the rotor current at rotor conductor will become zero, no rotor magnetic field flux will be produced by the rotor three-phase induction motor when the rotors runs at synchronous speed. And since there will be no flux produced by the rotor, so net torque produced by the induction motor will become zero. So, three-phase induction motor cannot run at synchronous speed. When the speed falls, the rotating magnetic field will cut the rotor winding and torque is produced. Now, we will study about slip. What is slip? As we know that the induction motor does not run at synchronous speed. So, the speed of rotor of three-phase induction motor is always lower than the speed of the rotating magnetic field or synchronous speed. So, the difference between the motor or rotor speed and the synchronous speed of rotating magnetic field is termed as the slip, and it is always expressed in percentage. So, normally slip can be defined as the speed difference between rotating magnetic field and rotor speed, that is ns minus nr, where synchronous speed, the formula for synchronous speed ns is 120 f upon p, where f is your supply frequency and p is the number of poles present in three-phase induction motor. So in percentage, slip is always represented relative to synchronous speed. So the final formula for slip is ns minus nr upon ns, where ns is your synchronous speed or speed of the magnetic field and nr is the speed of the rotor or speed of the motor. When any motor runs at slip s, then what will be the frequency of current or induced EMF induced at rotor? So it is given by Fr equals to S into F, where Fr is your rotor frequency, S is your slip, and F is your supply frequency of the three-phase AC supply, or the frequency at which three-phase stator winding is even supplied. Notice the importance. What happens? What will be the slip when rotor does not runs, or what will be the slip when rotor runs at synchronous speed? As we know that the formula for slip is ns minus nr upon ns. When rotors runs at synchronous speed, then rotor speed, that is nr, will become ns. So S equals to ns minus ns upon ns. So when rotor runs at synchronous speed, slip will become 0. And what happens if, what will be the slip if rotor is stationary? As we know that if rotor is stationary, then the value of nr will become 0. And after putting the value of nr equals to 0 in slip, the formula for slip is ns minus nr upon ns. And as we know that at steady state condition, rotor speed will become 0. It will become ns upon ns, and it will comes to 1. So the slip is a ratio and does not have any unit. Now we will discuss some basic question comes on this topic. So this is the example one. A 208 volt 10 horsepower 4 poles 60 hertz star connected induction motor has full load slip of 5%. Here voltage is given, line voltage is given 208 volt, power is given 10 horsepower, number of poles are given 4, and the supply frequency F is equals to 60 hertz, and slip is given 5%. What is the synchronous speed of this motor? As we know that the formula for synchronous speed is ns equals to 120 F upon P, where F is given 60 hertz and P is given 4. After putting the value of F and P, the synchronous speed of the three-phase induction motor comes to be 1800 RPM. After solving first part, we comes to second part, that is what is the rotor speed of this motor at rated load. So slip is given, and we also calculated synchronous speed, that is 1800 RPM. The formula for slip is equals to ns minus nr upon ns. We have to calculate nr. So the value of rotor or motor speed nm equals to 1 minus s into ns, where s is given in percentage 5%. We have to convert into fractional value, that is s equals to 5 upon 100, that comes to be 0.05. After putting the value of s 0.05 and ns equals to 1800 rpm, we get motor or rotor speed equals to 1710 rpm. After solving second question, what is the rotor frequency of the motor at rated load? So as we know that the formula for rotor frequency Fr equals to S into F, we have the value of S, that is 0.05, and value of F, that is 60 hertz. After solving this, we get 3 hertz. Then torque produced by motor equals to P output upon omega m, where omega m is the angular velocity of the induction motor, and it is given by 2 pi nm upon 60. We have the value of P output, that is 10 horsepower, and as we know that the SI unit of power is watt, so first we have to convert horsepower into watt, and as we know that 1 horsepower equals to 746 watt, so we have to multiply 10 by 746 watt to calculate, to convert into watt, and we already calculated Nm. So after putting all these value, we get the torque of the induced torque of the three-phase induction motor equals to 41.7 Newton meter. Now second question, a 220 volt three-phase 2-pole 50 hertz induction motor is running at slip 5%, Find the speed of the magnetic field in revolution per minute. You have to calculate the value of ns, and as we know that the formula for ns equals to 120 f upon p, we have the value of f equals to 50 hertz and p equals to 2. So after putting the value of f and p, we get synchronous speed or speed of the magnetic field is 3000 revolution per minute. After computing this value, we have to calculate the speed of the rotor in revolution per minute. We know that the formula for speed of the motor equals to 1 minus s into ns. We have the value of s equals to, that is 0.05. After putting this value, we get the value of motor speed, that is 2850 rpm revolution per minute. Now, third part, the slip speed of the rotor. We have to calculate what is the slip speed. We have the value of ns, that is 3000 rpm, and we have the value of nm, that is 2850 rpm. So as we know that the formula for slip speed is ns minus nm. After putting the value of ns minus nm, we get the value 150 revolution per minute. And the D part is the rotor frequency of the induction motor. So the formula for rotor frequency is Fr equals to S into F. And we have the value of S, that is 0.05, and F equals to 50 hertz. After putting this value, we get the value of Fr equals to 2.5 hertz. Hope the concept of slip are clear now. Now let us come to our next topic, torque slip characteristics. How torque of three-phase induction motor changes when slip changes. The torque slip curve for induction motor gives us the information about the variation of torque with respect to slip. So the formula for torque equals to Ks R2 into E square 20 divided by R2 square plus Sx20 square, where K is the constant, tau is the torque produced by motor, S is your slip, R2 is the rotor winding resistance. There are two winding, stator winding and rotor winding. Stator winding is represented by suffix 1 and rotor winding is represented by suffix 2. So R2 is your rotor winding resistance, where E20 is your induced EMF of rotor at standstill condition when your motor is at rest, and X20 is rotor winding reactance, and the formula for NR equals to NS into 1 minus S. As we know that the minimum value of slip is 0 and maximum value of slip is 1. So we have to first calculate the value of rotor speed when slip equals to 0 and when slip equals to 1. So when we put the value of slip equals to 1, we get the value of NR equals to 0. That means at a starting condition, when slip is equals to 1, your rotor speed is 0. And when we put S equals to 0, that means slip equals to 0, the value of rotor speed equals to NS. It means when slip of three-phase induction motor is 0, at that time the speed of the rotor is equals to the synchronous speed. Now, torque slip characteristics is subdivided into mainly two regions, low slip region and high slip region. In low slip region, the value of S is very small. This is around 0 to 0.006. So as we seen here, the value of S is very small. So the square of S square x2 0 sx2 0 square, product of sx2 0 square is much lesser than r2 square. So as compared to r2 square, the value of sx2 0 square is very less. In this case, we neglect x square x2 0 square. So torque, the formula for torque at low slip region will become ksr2 e square 20 upon r2 square. Now here we see that torque at low slip region, torque is directly proportional to slip. That means at low slip region, as slip increases, the torque will also increases. So here we see here, as slip increases, torque linearly increases, and it increases very rapidly. After attaining a maximum value, when slip enters into high slip region, the value of s square x2 0 square is much higher than r2 square. So at high slip region, r2 square can be neglected as it is much lesser than s square x2 0 square. So the formula for torque will become ks r2 e square 20 upon s square x2 0 s square x 20 square. So one s is cancelled from numerator. So torque at high slip region, torque is inversely proportional to slip. In this high slip region, as slip further increases, the value of torque decreases instead of increasing. So here we saw that the dotted line at high slip region, when slip further continue increasing, torque will decreases now, and when slip will become 1 after putting the value of s equals to 1, and when s equals to 1, as we know that s will become 1 when rotor is at standstill condition. That this is the condition of at standstill condition. So at standstill condition, we put the value of s equals to 1. The torque at the starting torque will become k e square 20 r2 divided by r2 square plus x2 0 square. This is your starting torque. Here, this is the starting torque produced at the time of starting. And at synchronous speed, when nr equals to ns, s will become 0. When we put the value of s equals to 0, torque will become 0. So at synchronous speed, the three-phase induction motor produce 0 torque. So this is the graph of torque versus slip characteristics. When we draw torque slip characteristics, slip started from 0 and end at s equals to 1. In this graph, we have certain points such as OA. OA is called stable region, where transformer three-phase induction motor works stably. AB is called unstable region. Point A is a maximum torque value, and at the slip, this torque will produce is known as SM, that is the slip corresponding to maximum torque, and the value of SM will equals to the R2 upon X2 0. Then point A is your maximum torque, point B is your starting torque, and point C is your full load torque. So induction motor normally work in region A to C region. Advantages of three-phase induction motor. What are the various advantages of three-phase induction motor? So the main advantages of three-phase induction motor are as follows. It has simple and rugged construction. It requires less maintenance. It has high efficiency and good power factor. It is less expensive and it has self-starting torque. Disadvantages of three-phase induction. The following are the disadvantages of three-phase induction motor. The three-phase induction motor are constant speed motor, hence their speed control is very difficult. We cannot vary speed very easily according to our requirement. Three-phase induction motor have poor starting torque and high inrush current. That means at the time of starting, it takes 4 to 8 times higher current than full load current at the time of switching. They always operate under lagging power factor during light loads and they operate at very worst power factor at heavy loads. These are the disadvantages of three-phase induction motor. Application of three-phase induction motor. Three-phase induction motor are mainly used for pumps and submersible pumps, pressing machine, lathe machine, grinding machine, conveyors, floor mills, compressor, where is we need constant speeds. Thank you. That's it for today's lecture. Have a nice day.